Get started. So sparing no expense, we have Piotr all the way from over CMS who's agreed to come and speak to us on the null origin of the Ambitwistor string, or null string origin.
Okay, thank you very much. So let me start by thanking the organizers for giving me this opportunity and organizing this great program. So this is work in collaboration with Eduardo sitting right here. So okay, and the point was to try and understand a little bit of the stringy origin of this Ambitwistor string and CHY formulae. So let me start by giving you the pitch immediately. I'll be introducing to those of you who are not familiar with Ambitwistors or CHY or all these things. I'll be giving a few slides later, but the idea is that so you start from string theory, so say non-Bogotto strings, and if you do the usual low energy limit, you send alpha prime to 0, and then you quantize. This little h bar arrow here is supposed to mean quantization. You get, supergravity generically. You can do that in the other direction. You first quantize your strings, and then you get supergravity in the low energy limit. The puzzle that's been floating around and that I'm going to be talking about much is the fact that these Ambitwistor strings that give formulae for the scattering amplitudes of supergravity seem to share some features of an opposite limit of string theory, in which you send alpha prime to infinity. If you take your stringy amplitudes and you send alpha prime to infinity, Gross and Mende have shown how your string theory integration localizes on the solutions to the scattering equations, which are shared by both of these things. So now you may wonder, but what's these two arrows here? Well, it's just that there is an ambiguity in the quantization of string theory in general and in null strings in particular. And starting from the same classical theory, you have two ways of quantizing it, and one of them gives you some sort of high spin-like theory. It's not really well defined, so in Minkowski space it hasn't been studied much. Another quantization gives you the Ambitwistor string, which is a theory which is truncated to exactly the massless sector. So right, so that's the pitch I'm going to tell you.
What's the dotted line with the cross?
Yes, so that's supposed to mean it's going to be hard. It's supposed to mean well, you'll have your own opinion at the end, but I guess we would say that there's absolutely no obvious way in which you can find a correspondence between the Hilbert space here and the states and the Hilbert space in there. They're not unitarily connected.
In that picture, the Ambitwistor string that level is quantum. So
yes, you can just loop things.
You could put Ambitwistor strings on their own in the upper level, but there's no arrows connecting.
No, you have to. You wouldn't, because if you take h bar to 0, you land both of these theories land you on this same classical theory. This ambiguity was noticed in the 80s. So here's a short outline. I'll start out with motivating why this is an interesting thing and telling you a few words about Ambitwistor strings and CHY formulae and this sort of things. Then I'll come to the tensionless or null strings. I'll describe the quantization and the relation to tensile or tensionful strings. And also I'll say a few words about the connection with Gross and Mende. Okay, so is anyone here not familiar actually with? Right, I see new faces, so I'm gonna say a few words about these things. So this is the CHY formulae, Kipchazo-Heian, 2014. I thought it was 13. So they came up with some formulae to write down amplitudes in gravity, gauge theory, and scalar theories of this form. So you have some sort of worldsheet integration over n positions of punctures like that correspond to the states that you're scattering. You have a product of delta function that completely fix this integration. So contrary to string theory, where the punctures would move around, here they're entirely fixed by this set of equations, of which we've been talking about much. And you have some sort of integrand, which tells you essentially the structure of the theory, which gives you the structure of your theory, gravity, gauge, or whatever. So here the k's are just the null momenta of the incoming or unscattered particles. Right, and so you have, generically you have n-3 factorial solutions to these equations, and each of them are individually absolutely awful, but when you sum them all, you get a Jacobian because you're inverting the delta constraint. When you sum them all, you get quite magically an n-point field theory amplitude. So Mason and Skinner came up extremely quickly with an explanation for these quite striking formulae, and they explained that they originate from a new sigma model that they dubbed the Ambitwistor string because it lives in Ambitwistor space in some sense. It does live in Ambitwistor space, but let me not go into this. So it's a first order. So you get just one derivative. It's a first order sigma model. P and X are the momentum and the position of the string. They are holomorphic, and it's subjected. You have two constraints that you're gauging. You're gauging the stress tensor of your CFT and this p squared constraint that appears here with the Lagrange multiplier E. And essentially, this p squared constraint tells you that you're considering as equivalent any two positions that are related by some p mu that is actually p squared equals 0. That's essentially the Ambitwistor case. So right, so when you gauge that, when you quantize this theory, you introduce your BRST operator and BRST charge and all that. You realize that the spectrum is type 2 supergravity for the model that has two RNS fermions, is anomaly free in 10 dimensions, and yes, again, this is alpha prime equals 0 of string theory in a sense, at the level of the spectrum. And the great thing is that it allows to put, so the CHY formulae were on the sphere, but you can now put this model, this sigma model on higher genus Riemann surfaces, and you compute loops with this. So this was done by Tim, Eduardo, David, and then Tim and Eduardo at loops later. So I'm gonna spell out a couple of mysteries that are linked to all this, unless there's a question at this point. Right. So again, this Catching equation that comes from the constraint p squared equals 0. They govern the saddle points at alpha prime goes to infinity of string theory. You have some exponential of alpha prime times some function, and when alpha prime goes to 0, you do a saddle point approximation, and this saddle point approximation lands you on this conditions at tree level, but also in loops, which is a little bit, you've got. Right, that's a technical point, but it works also for loops. So the mystery number one is, of course, like I said, why is it that alpha prime to 0 has anything to do with alpha prime to infinity? Well, I kind of told you already, but that's the sort of questions you would want to answer. Mystery number two, in a sense, once you put your theory on higher genus surfaces, you start to introducing loads of stringy mess, let's say. So these poles, this 1 over zi minus zj, get converted to some quite annoying elliptic functions. So we've been arguing yesterday that it's actually not that bad, but it is still the case that in string theory, the Fourier expansions of these theta functions do correspond exactly to the propagation of massive states. So one may be wondering, well, in that theory you have no massive states, so why do you introduce all of this junk? You're comparing for the same parameterization. If you were to go to a parameterization in string theory where you would not have elliptic functions, but, well, you have to have elliptic functions, but like Weierstrass functions or something, it would be less transparent. But if you compare both models with this parameterization, you have a Fourier expansion in both cases, and in one case you have massive modes, and the other one you don't have it. So why is it? Well, I'm not going to say anything on that, but that's the sort of question you would want to understand by looking for a string theory origin. Also, and more importantly, I'll be coming back on that. I'm not sure how it connects here. I'll say it later. So mystery number 3, or maybe just fun fact number 1. Again, what we've been doing with Yvonne, Ricardo, and Lionel was to explain how actually you don't need all of this stringy mess. You don't need all of these Fourier expansions, because you can do integration by parts in the moduli space of these objects that land you to the boundary where where the cycles degenerate, so where they're pinched. So you're supposed to think of that picture as this one here, where you have been pinching all of these external cycles. So what you obtain is a sphere with points that are connected towards one another. And funnily enough, that arrow here, which is an integration by part, also looks very much, at the technological level at least, technical level, looks very much like the filter limit of string theory. And you know, why is that? Well, maybe it's actually obvious, but it's still an interesting observation. So all of this motivates to look for an origin in string theory, and that's where we go. Okay. So let me recall a few things about the normal strings, Namugoto strings. So the Namugoto action is just the area that is swept by the string when it propagates in space-time. Okay. T here is inverse alpha prime. It's the tension of the string. Psi are just the coordinates on your worldsheet, and G is the pullback of the space-time metric to the worldsheet. So sorry, the determinant of this G alpha beta, and G alpha beta is just this simple, rather simple matrix. So, and yeah, again, X are just maps from your worldsheet to target space. So these are the coordinates of the string. So how do you take the T to 0 limit, which is what I'm trying to tell you about? Well, you don't really do it here, right? Because otherwise your action is just 0 and there's not much you can do. So one option is to go to a Hamiltonian formulation. The Lagrangian here is just the square root of G on the previous slide. So you introduce canonical momenta and you write your action as Px dot minus some canonical Hamiltonian. At this point, the tension is not present here anymore. It's just somewhere in here. Well, it turns out that for theories that have reparameterization invariance, the canonical Hamiltonian vanish, and it's just a sort of consequence of the fact that your time evolution should not depend on how you've parameterized your worldsheet. So the Hamiltonian is just governed by the constraints, because at this point, when you realize that your canonical Hamiltonian is 0, you actually have to have first-class constraints, or primary constraints at least. And these two constraints turns out to be these conditions. So they just come straight away. You take the derivative of your square root, you find P. It's quite, it's this expression. It's not particularly illuminating. But if you dot it into x prime, or if you square it and add this term, you get 0. So these are the two constraints that combines to the Virasoro constraints in string theory, and your Hamiltonian is now given exclusively. It should be H canonical plus the constraint, but H canonical vanishes. So you just have these two constraints and two Lagrange multipliers. And choosing lambda and mu defines a coordinate system on your worldsheet. So it's a gauge choice. So the action is now written Px dot minus H, and it then takes this form. So you have the Px dot term, you have the Px prime term that comes from here with this mu Lagrange multiplier, and lambda that enforce this constraint. Now it's very easy to take T to 0. Oops. Okay, just one word before. If you want to go, at this point you can go to the Polyakov action by just introducing this auxiliary metric H made of the mu's and the lambdas, and T as well. And right, so and then you could quantize you could do the path integral over the matrix, and you obtain you do your usual stringy business. You can take T to 0 now in this action because it just appears here. So you just drop one term in the constraint. You can also already see from looking at this H matrix here that at T equals 0 it becomes degenerate, and that's actually the case. So you can rewrite. Now you set T to 0. Okay, you rewrite. Your action is like so. And these guys have found a rather nice way to rewrite this action in terms of a vector density instead of the metric, the auxiliary metric that we had before. So you now have this field V alpha, and V alpha V beta is the sort of analog of H alpha beta. And the equations of motion for v alpha tell you that this object here, d alpha x, d beta x, has a null vector. That turns out that's the pullback of the space-time metric to your worldsheet, right? So what this tells you is that it's exactly the definition of a null string, of a null surface, that this metric here has determinant that vanish. Hence the name null strings, and Schild in the late 70s studied introduced this model. Question? Okay, so the open question is, like in string theory, we know that the path integral over the auxiliary metric gives you a reduction from the space of all maps to the moduli space exactly. An open question is, what does the path integral over the v alpha, this vector density, do in that string? And answering to that question normally should give you should allow you to understand what exactly is the integration cycle, or what exactly is are you integrating in the Ambitwistor string. So obviously at tree level the answer is known. What you're integrating is over some contour that goes along the solutions to the scattering equations. What is the analog statement at higher loops is not known. This guy started out the program. I mean, started out to try to understand this path integral in the 90s, but gave it up somehow. And funnily enough, is in Nordita. So we could have a. I mean, I could have a chat with him last week. Eduardo couldn't because of some plane strikes, right? Anyway, so yeah, we're working on that, and I think it's a very promising direction. So let me tell you a bit about the classical analysis of this null string. You can fix a gauge in which you set lambda equals 1 and mu equals 0. Okay, so you get rid of this, and you set lambda equals 1. Oh, I'm sorry, I forgot to mention that to get from here to there, you've got to integrate out p. Right? You complete the square, and then it spits out some squares of x, and that's how you do that. Sorry. So when you set lambda equals 1 and mu equals 0, you get an action that is simply the same action as for a free particle, except that it's still subject. It does still have two constraints. One of them being intrinsically stringy. This one here, and you can see these two constraints are the equations of motion for v alpha. So the equations of motion for that action is x dot equals 0 and x prime squared equals 0, which means that the sort of free particles propagate at the speed of light. In addition to that, so they propagate on the light cone, which is what this little drawing is supposed to represent. In addition to that, you've got to have that the velocity of your string, the momentum of your string, is orthogonal to the direction of the string itself. So that's the stringy constraints. That's what makes this action not just a free particle action, but something a little bit more. And that's what the little blue arrows here are supposed to represent. They're supposed to be perpendicular to the string. Okay. So now let's go to let's try and see how we can obtain something that resembles more the Ambitwistor string. So it's actually a gauge choice that will land us there, but it's a singular gauge choice, and some consideration on the constraints. So you fix first mu equals 1 and lambda equals 0. We keep the sigma periodicity of the string, right? It's still a closed string, so we want to go back to where we were when we shift pi to pi. So we obtain this action, which is very close to the Ambitwistor action once you complexify it. And in the second order form, if you integrate p out in here, so you don't fix lambda equals 0 yet, but you just integrate p out at mu equals 1, the action takes this form. So you can see here that lambda goes to 0 is a sort of a singular limit. And there is a heuristic argument, I'm not sure what it's worth. 1 over lambda appears here as some sort of 1 over h bar it kind of feels like a loop counting parameter in a sense, but it's pure gauge at the same time. So can you actually see from that observation that you can fix it to any value you want? So in particular, you can fix it to 0, which forces you to localize on some classical solutions. I don't know. Well, there is something to do with this, the fact that this gauge is singular. Okay, so so now we fixed the gauge, and we want to know what is the leftover gauge freedom after fixing this gauge. In string theory, this is conformal transformations, right? You can rescale, you can transform z and z bar by any functions of z and z bar, holomorphic functions of z and z bar. In the
What are the original symmetries of your action?
sorry?
What are the original symmetries of your action?
Well, you have this p squared that translates you that translates the x's.
So that's the starting point. That's
Sorry?
Is that the starting point? I just don't know
Yeah.
what your starting point is.
Yeah, that's the starting point. Yeah, this action here with these two constraints, px prime and p squared.
Okay, so you're not starting with the V action. That's
No, it is the V.
Well, yeah, it is.
That's part of the form of the
So after fixing this v, v transforms as a vector density. So you take your v action and you look at the diffeos that keep the v action invariant in a certain gauge. And so when you fix it to this Ambitwistor gauge, the diffeos are of this form. So it's not conformal transformations. You can reduce this. You can understand that this diffeos actually. You can group them into operators that form a VMS algebra or Galilean Conformal Algebra. So these guys would be essentially the modes of this guy would be super rotations, and the modes of these would be super translations. I'm going to say a few words on that later. Right, so now let's look at the constraints. The goal is to just recover that the modes of your constraints satisfy the same symmetry algebra, the same algebra as the one that we found before. Right, so you take your gauge fix action. The equations of motion simply tell you that p and x depend on sigma plus only. The constraints, well, are still the same. So you can expand in modes p and x. That they have classical Poisson brackets, standard Poisson brackets, and essentially in that gauge, the constraints p of x prime and p squared have the following mode expansions where L, let's write what L and M was, where, so L, the L ends is something like the sum of the x and p n minus n, and mn is so the p n minus n. And so it's quite straightforward to see that this guy obey this algebra here, which is once again this Galilean conformal algebra, not to be confused with the Schrödinger algebra. It's got an infinite number of these constraints, of these modes. Sorry. So the L satisfies some 0-0 algebra. With M, they just give split M, and the M's commute. And this is the same algebra as the one we would find here if we were to expand the AC mode, which is expected.
Sorry, this constraint p plus x.
Sorry?
This second constraint apart from p squared, that is not the argumenting tensor, or is it in your choice?
Yeah, that's the point. That's the point. So at this point, the actions are equivalent after Vic rotation or complexification, but the constraints seem different. In the ambiguous string, you would be gauging pdx, where d would be d plus x, and here you seem to be gauging px prime. But so we have several arguments in the paper to say why these two constraints are actually the same once you get in that gauge. I'm going to give you one here, which is rather direct, which is that this constraint p dot x prime. So you can rewrite the sigma derivative as a difference of d plus and d minus, and on shell d minus x is 0. So on shell the two constraints are equal. That's one way to see that. Once you get to this lambda equals 0 gauge, you can actually call this your stress tensor. But it wasn't the stress tensor before you reached lambda equals 0. So it's a rather subtle point, and I'm happy to discuss it more with you, but it's also important that, because it allows you to really consider that your sigma model is a CFT and not some sort of BMS field theory or Galilean Conformal field theory or something of this sort. Okay. Questions, or otherwise I'll proceed with quantization.
Is there a reason you chose this gauge except that you wanted to land on Ambitwistor?
Is that not a good reason?
No, I mean, it's not a good reason. Your starting point, and you use, if you want to say that you're quantizing a starting point, you should choose the usual gauge. Is there a reason why you chose this singular gauge?
Well, if you were to use other gauges, you would have difficulties in coming up with some vertex operators, formalism, or at least people haven't been able to compute amplitudes in the other gauge.
So the other quantizations are sick in something.
I don't know if they're thick. It's just that people haven't been able to get amplitude to write vertex operators to use state operator maps, or they were missing some CFT interpretation of their.
Sorry? The Hilbert space, the gap on the same in the gauge.
No, the quantization is
physical
the
states on the same.
quantization is the same, but it's just that if you want to compute amplitudes, they haven't been able to do it before.
Okay, so the states are the same on that.
Yeah. So here they are, by the way. So now the ambiguity in the quantization, the two arrows I was telling you about at the beginning. So you want to replace your Poisson brackets by commutators, and the question is what is the ordering you take for these products of P and X? Well, obviously the only important case is when n is equal to minus m. So in one case that is called Weil ordering, you put the p's to the right, and in the normal ordering you put only the positive modes to the right. Okay, and it turns out that this gives completely different quantum theories. The vacuum that you define by this choice of ordering is the one that is killed by all of the modes of P, because these guys are your annihilation operators. Okay, so for all n, this vacuum HS stands for higher spin. Is killed by these P's, and here it's killed only by the positive modes of P and X, and A stands for Ambitwistor, or that would be the null string. And the results are the spectrums and the quantum theories are really different. This one doesn't have a critical dimension. The mass spectrum, you obtain a continuous mass spectrum, which is, and people haven't been able to compute any sort of amplitudes until this morning, or what was this paper by Bakshi? I didn't have a look. Right, so that theory has a critical dimension 26 or 10, depending on if you look at the bosonic or spinning versions. It has only massless states, and in that nice gauge you can apply CFT techniques and really quantize your model, and really compute amplitudes very nicely. So I won't say much about that part of the slide, because there isn't much to say, I think. I mean, there isn't much to say. There hasn't been much done in the literature. In ADS spaces, there is much more to this. It's a completely different story, and people have been really working on understanding the alpha prime to infinity limit of string theory as some Vasiliev theory of some sort. And in that case, the story can be made much more neat somehow. So I'll only focus on this part here from now on.
The mystery number one sort of comes in here, right? So normally only massless states, and it will lead to supergravity amplitudes eventually. That's something we'd expect from the infinite tension limit of a string. Here you've been studying in both directions, both quantizations, the tensionless string. Yet with some particular choice of normal ordering, some particular choice of vacuum, you find the same thing that you would have expected. I mean, this is where the mystery number one comes in.
Yep, exactly.
Are you going to
Although
explain why I should have expected that this alternate route gets back to?
Yeah, a bit towards the end. I won't be able to tell you how you could take that theory and understand how by adding a little bit of tension you would be reproducing Gross and Mendel, but I'll say still a word in that. Okay, so here is a short review that I'm just gonna flash. It's just for the names of these people to be here. So it starts from quite some time ago, and there's been lots of development in that domain. Actually, it's kind of stopped towards the end of the 90s. But now there is this guy Bakshi and some students or colleagues that catched up on these tensionless strings because they were interested in some BMS flat holography, including one paper this morning by this guy. Okay, so now let's look at the quantized model and physical states and quantum algebra of constraints. Only the L's get essential extension, which you can see because, well, you know, it's a fact. In string theory, you would have L's and L tildes, both of them satisfying zero zeros, and that would come up with C over 12. So here you get a sort of doubled central charge. The interesting part is that you get a normal ordering ambiguity from reorganizing these P and X modes here of -2, and which tells you that that the physical states are only those for which L0 has eigenvalue 2. So you select only states with. I recall you that L0 is the zero mode of the P dot X prime constraint, which is the angular momentum operator. So you select only those states that have 2 units of angular momentum, and that's that's a Casimir energy effect, right? Like in string theory. This 2 here is actually some 2H bars. So you really select the quantization. Really gives you that's where the truncation of the spectrum comes from truly, from this -2 here. So from this you see that the physical states you get are essentially made of the first few modes of P and X, these guys, and that they correspond to some graviton, dilaton, and a B field of some sort. But the problem is that they all have zero norm, which you see immediately because, like, if you take this state and you square it with himself, the P commutes with themselves. So you can just take them through, and they have zero norm directly. So it's not a theory that explains. That tells a bit more why the bosonic theory doesn't quite work. The bosonic Ambitwistor string doesn't quite work.
Sorry, that doesn't seem to be the usual problem with the bosonic. What?
Well, you also have some other states that are not diagonal under the action of this M operator, and they all mix in some intricate way that in the end, do they have negative norm? No, they all have zero norm. Yeah, you have a non-diagonal action of this guy here, and when you try to diagonalize it, you realize that you introduce wrong sign commutators, operators with wrong sign commutators, and so you've got to add some i's to make the sign correct, and at this point you start messing up your theory completely. You have a different perspective on it, starting from the tensile sort of twisted quantization or normal ordered quantization, where you see that some states just degenerate to states you wouldn't want. I
will take that. So you can kind of put the tension back. You can do this different quantization with some parameters with the tension. So I don't see how you put the tension back. Because
we'll come to it later.
But there's some sense that spin 2 is not only one state, but it's 3 states that collapse.
Well, but that's not. Yeah, well, that's one thing, but. What do you do with your theory that has only zero norm states? Can you really?
No, I don't know how to do this. I'm just saying the usual Ambitwistor bosonic string. I thought it just has the wrong interactions, but it has physical states in it.
Well, okay, yeah. I guess one should investigate more closely what are the sort of gauge transformations of these states. It's not exactly.
So which state is C dx?
Dx, right? Dx is a state. Yes, that's right. Dx is a state, but this guy is not diagonal under the action of this n constraint. So what can you say? dp is a state as well.
But those states that you've written down are what you would normally have written down in.
Right.
I'm just worried. how are you defining your norm? In particular, is the adjoint of P obviously just P with the flipped sign of the mode, or could it be
you mean because you're in complex space now, or?
if you said that the
Are
adjoint
you
of
worried?
P was somehow F, the mode of F, then these wouldn't have zero.
Huh. But so you mean it's about the out vacuum?
D bar x.
Sorry?
Yeah, so you're saying that P and dx are somehow conjugate,
I'm saying
or
that
D bar
I'm,
x.
I'm defining a norm such that P subscript n dagger is x minus n.
You call the final norm whatever you want. But if you're a Lorentzian signature and you ask your action to be real, then under that norm, that has zero norm. So you have to come up. You can. So in that way, you come up with a different inner product for a Hilbert space.
Well, I mean, I think Nathan's question is the normal bosonic ambitwistor string with those vertex operators. You scatter them and you get some answer. It's not zero.
Yeah, sure. But
How's that compatible with the idea that they've all got zero?
But what is the norm that you will use in the Ambitwistor string? What is your CFT state? It is not just the usual norm that you get from the CFT, because that will be just getting the P dagger, which is the P minus.
So there are states with positive and negative norm in the theory. You're just saying they're not, none of them are physical? Is that the point?
No. Oh, yeah, sure, yeah. All right, so let's go to the one that is well defined, and I'm happy to continue the discussion on the bosonic one later. So if you add your pair of real fermions, you go to some RNS-like model, and you modify your constraints in some rather straightforward way. You run the quantization again, and you realize that your spectrum that could have been made of the states p minus 1 and psi minus 1/2 is actually truncated down by some sort of GSO-like projection to only that state here. So these indices 1 and 2 are just for A. I didn't write Lorentz indices, and then you find your type 2 supergravity spectrum at this point. Right. So any further questions or? Okay, so I'll go to with the relationship with tensile strings. So for normal strings, your X field is decomposed in left and right movers, alpha n and alpha tilde n. That come with z and powers of z and z bar, where z is just the exponential of tau and sigma. So if you want to try to relate this to the model we were dealing with before, you need to find a way to map the alphas and the p and y and x's. So one way is to do like so. So for p and x, you take the normal commutation relations, and then the alphas are just also have the normal commutation relations that they should have in string theory. And in terms of these modes, the Ambitwistor, the string theory vacuum is just the one that is killed by all the positive frequency oscillators. The Ambitwistor vacuum is actually completely different. It's killed by the positive alphas and the negative alpha tildes. And you see that quite directly when you look at this here. If you put a minus sign here, all of these guys get pluses, and it's quite clear that you take the sum and the difference, and only the p's and the x's that have positive n kill the vacuum. So for those of you who have struggled with or read Siegel's paper, this is what they call this change of boundary condition, and yeah. So I suppose it is in a sense some boundary conditions, although I still don't quite see completely on what, but I suppose on your theory. But so that's it. So and now, where am I? So this is the difference between the two vacua, if you want. And that guy here, if you take your tensile theory and you apply that quantization condition, the Hilbert space you obtain is also truncated to something that I'm gonna talk about very soon. Let me just mention a few words about the generators, how you get the GCA algebra starting from the product of the two Virazoros. Well, that's how you look at these combinations of the ln and ln tildes, and so here they are written in terms of modes. You see that the m has some t dependent term, but the objects you get are just the ones that I wrote here, apart from the fact that I forgot some n. And an interesting comment that you can make at this point is that you would think that this this combination of L's, let's look at L0. You would think that this combination of curly L's actually in the difference, the normal ordering constant that R plus 1 in both cases should vanish. But it turns out that this L is acting on the twist on the different vacuum, right? So you want to flip the alphas and the alpha tildes inside the L. So you end up flipping also the sign of this normal ordering ambiguity here, and to plus 1. And in the end, you get the correct -2. You get -1, -1, sorry, minus plus 1, and then you get your -2 from that change of sign. So this transfers the normal ordering ambiguity from what was the mass operator in your string to the normal, sorry, someone help me. Sorry? No. What's this condition?
Level matching.
Level matching. So you transfer the ordering ambiguity from the mass to the level matching, and that selects only the state that have a difference of 2 in between the left and right. But don't think that you can then take any arbitrary mass level and just take 2 less for the opposite sector, because you have all of the other constraints to apply, and that's just another way to rephrase this truncation. Right, so these guys had actually observed that already some time ago, and yeah, Siegel commented on this. So now, what is the tensile deformation of this Ambitwistor string? Again, these guys had a look at it already quite some time ago, and it's supposed that tensionful deformation of the Ambitwistor string is supposed to be related to this rather mysterious HSZ theory, which is some sort of double field theory, but the state, it has the same states. I can't say much more because that theory is quite mysterious to me. So let me just talk about the deformation of the Ambitwistor string instead. So you take your p squared constraint and you deform it by some t squared dx squared constraint that has the correct conformal weight. And the vertex operators you write are those of the graviton, bifield, and dilaton. They get some t dependence, but you can also write two new vertex operators that correspond to massive states of mass plus minus plus tension squared, which are these guys here. And these are spin 2 states. They have zero norm or positive norm, or I don't remember.
One is positive, one is negative.
Right. So one of them has positive norm.
There's issues with the norm in.
Sorry?
There's issues in the bosonic form. There's issues with the norm.
Yeah, sure. Yeah, sure. So yeah, let's not continue that discussion actually. And so you obtain these 2 additional states, but when you send the tension to 0, they all collapse onto this sort of spin 2 vertex operator that doesn't give, like you said, the right interactions anyway. So there is a rather interesting question, which is to know what the delta function on that constraint gives. Probably not. Okay, probably.
Sorry, I have a naive,
Yeah.
stupid question. Does doing this tensile deformation, there's now an XX in P?
Sure. You can't you can't integrate alt
I
x.
don't see how to.
No,
I
no.
don't see how to get that constraint.
There's no x-axis.
Why?
So okay, so P squared into the X.
Well, you will have an effective vertex, I suppose, but you won't be able to integrate alt x.
I just have a very stupid boil it down to where does k squared equals 4t squared come from. So you get a double pole when p squared goes into the exponential, but then
Well,
it looks like you get a quadruple pole from p squared into dx dx. So why?
Okay, hold on.
If there was an xxop, then
Yeah.
you could see that the dx's in the deformed Hamiltonian would go into the dx's in the kind of vertex operator. It's not an important question.
There's no.
You would see that from the you will see that from the modes. If you apply your constraint to the modes, you would see that the mass operator has a p squared inside, has a k squared inside, and you would see from it that for this constraint to vanish, you demand that k squared should be minus 4t squared. So I suppose.
Is my question just too naive?
No, yeah.
Well, you would-
It cancels off. That pole you wrote, it cancels off and you get exactly what.
Okay. Okay.
So, right. So, what would this constraint give? Probably not much actually, because the nice thing with the Ambitwistor string is that you can do completely the x path integral that gives you that p is some sum of k's over z minus zi, and that comes from integrating out x in the path integral. Here, since x now enters the constraint, you can't get rid of it anymore. So it probably gives you something like in string theory that you have to define your. You probably lose localization completely, because now you have to define an integration cycle just like in string theory. You would have to do so by imposing the 0-0 constraints, and but that's an interesting question. Okay, so just a few words on Gross and Mende, and then we can go to lunch. So the reason why both theories share the scattering equation in a sense is just because they both share this p squared constraint. In the Ambitwistor string, the constraint imposes the reduction, like I said, the constraint imposes a reduction to the scattering equations. And in string theory, the fact that you're sending this t to 0 at high energy is sort of very consistent with the fact that your integration over the whole moduli space gets squeezed in a sense onto the solution to the scattering equations. Is there could be more to say? I'm not sure. It remains to be completely elucidated. But that morally, that's the reason why they share this scattering equation. So coming back to some question that David was asking, I suppose. One thing that one would want to do now is to look at this at the Gross and Mende limits of the diagram, but in the opposite direction. Can you take your highest spin theory and add a bit of tension to it and do something? The thing is that if you start with your highest spin theory, you don't have a nice you don't have the nice CFT that you have with the Ambitwistor string. You don't have your PD bar X CFT because well, because this vacuum condition, the fact that the Pn, all of the P's kill the vacuum, but not the X, just prevents you from using the usual, from repackaging everything into your usual conformal fields. So you have this theory, and you would want to add a bit of tension to it, but it's really not obvious how you should do that. And in any case, it's not going to be perturbative, because if you look at the high energy regime of string theory, it's exponentially soft, so you have exponential alpha primes times some stuff. And so T comes in with an inverse power. And if you want to treat T as some sort of coupling, that's very non-perturbative. You're not going to see that in some T expansion. So maybe there is something to do, but it's not obvious. And what happens to this continuous spectrum in that context is even less. So let me end with some more optimistic views. One thing I think is really interesting is to understand this path integral over these vector densities that will tell you exactly what is the moduli space of your Ambitwistor string at higher loops. This point I'll talk about in the next slide. That I won't talk about, and that neither actually. So just to conclude, let me show you again this diagram. There could be actually maybe some arrow that would go from here to there, because there is this fact that the Ambitwistor action is a complexification of the world line action. World line action would be p dt x integrated on some world line, and the Ambitwistor action is p d bar x. So it could be that there is a way to go from here to there directly, but if one asks the question, why is it that this Ambitwistor string computes the same things as this limit here? Well, I'm not sure what answer to give. It's a fact that when you quantize this object, spinning object, you have the same spectrum. You have the supergravity spectrum. You have a theory that makes sense because it's a well-defined theory. It's a CFT. You have your BRST charge. So it's supposed to reproduce the interactions of supergravity. So it has to compute the amplitudes of supergravity. The same is true here. So it could be just a coincidence that both have the same spectrum and both are consistent theories, hence they compute the same things. Or it could be that there is something deeper, I'm not sure. So thank you.
If you take a tensionless limit of a normal string, then the picture is of something incredibly floppy, and so it's sort of perfectly reasonable to expect it will have a continuous mass spectrum and all this sort of stuff. Whereas what makes the Ambitwistor string much more akin to an infinite tension limit is the fact that it's chiral, or holomorphic. Globally, holomorphic maps from a compact Riemann surface are tremendously tightly constrained, right? They're even more constrained than harmonic things. You just can't with it at all. So that, in that sense, it's much more like a... Now, it could be that one of these quantization schemes that you discussed, the null string, is somehow compatible with that chirality, compatible with that holomorphy, maybe not just in the worldsheet sense, but a sort of holomorphic polarization of the Hilbert space, and the other one isn't, and it's that holomorphy that's really making the difference.
Well, I'm not sure what else I can say. When you take that object, the rigidity comes from this quantum effect that you get this normal ordering ambiguity that freezes you to only states of conformal weight 2, and that's where the rigidity comes from. The chirality also comes from here
It's
somehow.
not just that, right? It's also there's no XXOP, because you might have in normal string fields the same story would say you're frozen to conformal weights 1,1. But there are infinitely many of them because you can play around with the conformal weight of ECIK.x. Here you can't.
Well, sure. I mean, yeah, that definitely is true. But
Just for that, from the CFT, you're asking this those conformal fields X and P should be holomorphic the origin.
I'm not sure the holomorphy on the worldsheet is quite the holomorphy I have in. I understand that that's true kind of in both.
Yeah, but I mean, the things that both views that you said just have the same classical limit. So your classical intuition, I don't know if it's not very good to actually give you exactly what you expect from the quantum theory, but it's just a fact that you have two different factori and you have different central terms for this two factor, not more than
they used to speak about some sort of instability as well. I'm not sure if it's completely correct, but you have something that when you quantize makes it chiral, that you select only the states and then it becomes just holomorphic maps.
But in both cases, the classical equation of motion tells you the same thing about it. They have the same classical equation of motion, right? So your floppiness or not of the worldsheet classically is the same for both models. So
Yeah, well,
That's really a puzzle. Because, well, okay, but that, I mean, that's a puzzle for the null string. But one thing I am sure of is that holomorphic maps are very, very rigid, either classically or otherwise.
So are you less puzzled if you look at this theory here that has this quantization condition? So the z bars are the fields that depend on z bar are regular at infinity, and the field that depend on z are regular at the origin. It also is a very rigid theory. It has just this very few states, and actually in the case of the superstring, if you apply the same quantization conditions to the fermionic oscillators, you obtain a theory that does not depend on the tension at all. So it's just a random parameter in your theory. It looks as though it's deformed, but it's just a fake parameter. There's no t inside. So what and still it seems like you can formulate this theory in as a non-chiral theory, but it's hidden inside.
Your question is related to this when from the dx prime to the rx constraint when on that gauge choice. Because that only happens when in the lambda equals 0. And I think it's related to that. Is there a tensile deformation of the superstring? Yes.
What do you mean?
What is it?
The tensile. Oh, it's the same. Well, up to technicalities, Eduardo. Up to, so the bosonic constraint will be deformed like that, and the super constraints. Yeah. So you've got to look at essentially they descend exactly in the same way. If you look at your G.
Tell me what theory it describes.
Sorry.
Tell me what theory. So when t equals 0, it's supergravity.
It's also supergravity when it's deformed.
How does it depend on t?
It doesn't.
Then my second question. Is this the limit of anything? You say it's alpha prime goes to infinity or t goes to 0. Is that the accurate statement? Is it t goes to 0 of something?
What theory are you talking about?
Well,
the deformed
I know
super?
what the string theory means at alpha prime non-zero. Well, I know what it means at 0. I don't know what it means at alpha prime goes to infinity, but I know what it means to take the limit as alpha prime goes to infinity. That's not what you're getting. So I'm asking, is this the limit of anything? So if you say it doesn't even depend on t, then I would say that's not even the limit of anything.
You talk about X and Z.
No, the superstring.
Well,
you said the superstring doesn't depend.
classically.
I'm asking classically. I'm asking this.
So quantum mechanically, well, it's a parameter that is just.
Is it the limit of anything? That's what I'm asking.
No, in that sense, no. It's not a limit. It's just an isolated quantum theory.
Then I would say it's just alpha prime goes to 0. That's the way we already understand it. Why do you insist that it's something else? It's not isolated. It's the
But
string
what?
goes to 0.
Why?
The supergravity is the string when alpha prime goes to 0. Supergravity is not the string.
But why do you say it's a string theory and not a world-line theory then, for instance?
String theory when alpha prime goes to 0 is a theory of supergravity.
Right.
String theory when alpha prime goes to infinity is not a theory of supergravity.
Right.
That we know.
Right.
Your theory is a theory of supergravity. So why do you insist that it's alpha prime goes to infinity? That's what I don't understand.
Well, but what's there? What?
Maybe we can discuss it with
I'm not sure what else.
If it's to say start
You have these
with
two
alpha prime
quantizations.
goes to infinity.
No, but there's no goes to. That's what I don't understand.
Well, but
It's not
then-
a goes to. It's just an isolated point, as you say.
But what's wrong with what's wrong with that? I mean,
If it's an isolated point, we know what that isolated point is. It's supergravity. I just don't know why you call it alpha prime goes to infinity.
well, because you want to see where this why do you have the scattering
can
equations
start
or
with
yeah.
Another question. So this L0 minus L0 bar doesn't annihilate the physical states. In string theory, usually this is important because in order you can match vertices together, you need to have, this is an important constraint. So can you comment on that? This L0 minus L0 bar.
Well, it's just telling you that your state should be conformal. Should have conformal weight too.
Well, this is geometric interpretation of the rotation of the.
You mean why do you have
There is no L0 bar, it's L0 tilde. It's got nothing to do with right movements.
Oh, you shouldn't.
There are no right movements. It's chiral.
But it does allow for the scattering equations to be split too.
yeah, in a sense, I suppose.
I was just going to comment what Nathan was saying. I mean, it seems to me, I mean, if you consider string theory, whatever sort of string theory you like, at extremely large values of alpha prime, finite but extremely large, you have vast numbers of low mass states.
Mm-hmm.
So it doesn't look anything like what you're talking about. It seems to me.
I don't know what else. I don't know how I. Let me try to rephrase it. Oops. This is the theory you're talking about. That thing here is just not the same quantum theory at all. It has nothing to do
What
with.
I'm saying is that what you're looking at is not a large alpha prime limit of string theory.
Well, have I said? I'm not sure I've said that. It's. you know.
That was what the diagram was showing up there. Did you say alpha prime?
No, that arrow here is quantization.
No, the horizontal arrow.
Horizontal arrow is classical.
Or even classically.
Classically, it is.
But classically, you're still going to have large. I mean, there is little difference between.
Well, okay, but why are you interested in the classical theory? When you quantize it,
I'm not interested in any of it. I'm just quarreling with your words in interpretation. It doesn't matter, but I just don't see
It matters. You
the
can
same
have
sense.
you can have different quantum theories with the same classical limit.
Of course you can. But this is the question of whether this is in any sense to do with the alpha prime goes to infinity limit of string theory.
Of the real string.
it
no.
isn't. It
No,
isn't.
no, that's the point.
It isn't.
It's not connecting these two things.
Well, there is no arrow here. That's the point.
Sorry, I don't think how.
The sort of blank space here is supposed to be that, you
I
know.
know that classically the equations of motion 1 are incredibly rigid and the equations of motion 2 are incredibly floppy.
Well, also, there's tons of paper in the literature that have been completely obliterated from that. They have been understanding that if you quantize your null string, you obtain only supergravity. They could have gotten the scattering equation 30 years ago if they had come up with the CFT formulation by quantizing this null string, and then we wouldn't be wondering about if it's a null string or not. It would be common knowledge for everybody that you can quantize your classical string in two different ways, and you know there are some further questions, but I think so. Let me emphasize again this fact that if you want to understand what's the moduli space of your theory at loop level, if you want to understand if you have modularity or this sort of things, you need to understand how you quantize, how you do the path integral over this degenerated metric, and that you're not going to do that from string theory. You're not going to do that from supergravity either. So if you want to understand if the theory, you know, can be defined completely from first principles at loop level, that's how you have to do it. So I suppose that's okay. That would be the best answer I could give to your question. Why should anyone care? Well, because one would really want to understand if you're integrating over the moduli space or over some different space, Teichmüller space or whatever. Am I making this point more clear, or?
I think we're talking somewhat at different angles. It's a question of what words you're using.
Okay,
the
so
question you're giving. I mean, well, never mind. We can talk about it later.
okay, let me rephrase one last time because I think it's really important. when you look at your theory at loop level, you really want to understand if you're stuck in the moduli space or if you're stuck on the full Teichmüller space or this kind of things, and that you won't understand by just using the CFT actions because nothing tells you where you're supposed to integrate. So I'd say that this is the really important question for me. And I agree with the fact that it's supergravity anyway, so okay.
Okay, so if there are no more questions, let's thank you.